Now I'm recording. Good save, Aaron. Also, I've got this lecture recorded from 11 o'clock too, so let's see. Okay, so here we got B, A was equal to 0, so B goes to 1, right? Then here on the next one, A is equal to 1, so that means B is 1, A is 0, so the next one is going to be, it stays the same, right? It only toggles on the next one. Then here we have B is 1, A is 1, so that means A is 1, so B has to toggle, goes to 0, so we get this sort of doubling up effect, 1, 1. Now if we look over here, C is going to update, it's only going to toggle when we have B and A, right? So we have B and A, so 0 and 0 is 0, which means it stays the same. 0 and 1 is 0, which means it stays the same. 1 and 0 is 1, which means it stays the same. And then finally, 1 and 1 means that it toggles, so B and A, 1 and 1 is 1, so C needs to toggle, so that's 1, and then of course it's going to stay all the way down to this last one, where here finally we have 1 and 1 again, so that toggles. Here we had a B equals 1 and A equals 1, which means A needs to toggle, and A is always going to toggle, so it goes back to 0. So here we can see, if we sort of trace that behavior through the circuit, that we start at 0, we count 1, 2, 3, 4, 5, 6, 7, and then go back to 0. So are there any questions about that behavior? Cool. Okay. So next up, let's do the same counter, but we're going to do them with D flip-flops instead of T flip-flops. Now this is going to require more hardware to do. We're going to have to use more logic gates, but the design process is a little bit simpler because it's basically exactly what we're used to. For our D flip-flops, we can choose to just totally ignore. We don't need any flip-flop input equations because remember, D flip-flops are transparent. The next state just passes through, right? A T flip-flop is not transparent because when one happens, other things happen, right? There's some logic that happens inside the flip-flop itself, whereas with D flip-flops, the signal just passes all the way through. So we really only just have to treat these guys as their own separate things. So I can say C plus is a function of C, B, and A, and is equal to the sum of minterms, 0, 1, 2, 3, 4, 5, and 6. And B plus is equal to a function of C, B, and A, and is equal to the sum of minterms, 1, 2, 5, and 6. And A plus is equal to a function of C, B, and A, and is equal to the sum of minterms, 0, 2, 4, and 6. Right on. So we derived these functions for C plus, B plus, and A plus, like we've been doing for combinational logic circuits the entire semester. Are there any questions about how we derived these Boolean expressions? Hopefully that should be pretty old hat for you guys at this point. Okay. Boom. So we take these guys, we throw them into our K-maps. So let's start over with DA because it's the easiest, right? We're just going to create a group of 4 right here, and we'll see that A is just equal to what? 0 and 0. A is equal to A prime. We're going to get that toggling effect on A that we need for our counter. So that's kind of to be expected. Now for B, we've got a group here at 0, 1. So that's going to be, so we'll say, hold on, so A plus equals A. We'll say B plus equals B prime and A, or then down here we've got B and A prime. So B prime and A, or B and A prime, we now know is equal to B XOR A. And then finally for this last one, we've got, this diagram is a little bit confusing because it's, you know, this is a group of 2 and then it's also a group of 2 up there, but let's start here. So that's going to be, we'll say C plus is equal to C and B prime, or come up here, C and A prime, or just this guy by itself, which is going to be C prime and A and B, or B and A. We can do a little bit of simplification here. We can factor out the C from this guy. So C, actually I'm going to take this guy up here because I need a little more room. C plus is equal to C B prime or C A prime or C prime B A. I'm going to factor out the C, so I'm going to get C and B prime or C prime or C prime B A. Now here I can apply De Morgan's and get that C plus is equal to C and BA prime or C prime and BA, and hopefully we recognize this as an XOR operation, so this is going to be C XOR B and A. So there we go. This is just solving K-maps the way we've been doing it all semester. So from there we get our expressions. This is what we just had. A plus is equal to A prime, B plus is equal to B XOR A, and C plus is equal to C XOR B and A. All right, any questions about deriving those equations? All right, so now we go ahead and take a look at the circuit. I'm going to come to A last, but let's start with C. Right, we've got our AND gate here that's tied. Chase that all the way around. That's B. We chase this guy all the way around. That's A, so that's going to be BA. And that's tied to C, so that's C XOR BA. Now we look over on the B side. Here we've got an XOR gate tied around to A, and then we've got B. So we got B XOR A as we expected. Now here it gets a little bit weird. You'll see this convention done a lot in counters, right? A lot of times designers like to avoid using the complementary output of their logic gates. So instead of having A prime tied around to D, what they've done here is they've said, well, let's tie it through an XOR gate, right? Because remember that A XORed with 1 is going to be equal to A prime. Just like that. Just to kind of keep the logic clean, they'll do it that way. So that's why we have an XOR gate tied to A on one input and 1 on the other input. So there's our design for this binary counter, 3-bit binary counter with D flip-flops. Any questions about this guy? I know, Liam, they're making me nervous too, man. Because it must be a Friday. Because like I said, this class is, you guys are normally my talkative bunch, man. It's also cloudy and rainy outside, so maybe that's having something to do with it too. Physics test, huh? No energy. It's understandable. Physics test after this. So Matt's not even paying attention. Matt's just cramming for his physics test. I know I'm not wrong, Matt. I went to college. I know how this goes. Aaron's like, oh, dang, we have a test in physics. And yes, Joshua, T flip-flops in Minecraft are a thing. So let's move on. In that case, let's get through this lecture. Let's maybe get done a couple minutes early. So binary up-down counters is what we want to talk about next. So a binary up-down counter is going to do exactly what you would think about, which is, so here we've still got a 3-bit example, and we're still going to count from 0, 1, 2, 3, 0, 1, 2, 3, 4, 5, 6, 7, and then back to 0. But we're going to count up the numbers when our variable u is true, and we're going to count down when our variable d is true. So we've had this really kind of confusing to look at state table over here where we have our present state And then we have our control, what I'm going to call our control inputs. Right, U and D, and then that leads to our next state. Now we won't worry about deriving these equations. I won't expect you guys to be able to derive these ones because it gets a little bit tricky and you got to dig in. Basically, this is a 5-variable truth table, but there's a lot of don't care, so it gets kind of strange. But anyway, so we have U. Whenever U is 1, it's the binary counter that we just looked at, and we're going to see how that's present in the resulting function. Then, of course, when D happens, it's the binary counter, but it's going to run in reverse. And so what you'll see is everything that happens is happening on the zeros instead of the ones. So let's take a look at what we mean by that. So here we have A XOR U or D, right? So let's kind of unpack this one a little bit. So if we did that, we would say, well, A plus is equal to A, well, I take that back, right? So I'm just going to go down a confusing road. I don't want to do any of that. So A XOR, remember that A XOR 0 is equal to A, and A XOR 1 is equal to A prime. So what this says is basically, you know, if U or D is 0, means we're not going to count at all. We don't want to do anything. So A just stays the same, right? A doesn't toggle. Remember, A is the driver for all of this. If A is not toggling, nothing is happening. And then also when we're counting, no matter which way we're counting, if we're counting up or down, in both cases, the A bit is always toggling. So it doesn't make a distinction between one or the other, right? So as long as U or D is 1, A doesn't care. A is toggling. A is doing the thing. Now let's go ahead and take a look at B, right? Remember before it was B XOR A, right? Now here it's B XOR U and A. So if U is 1, then it is B XOR A. But if D is 1, and remember the control is that they can't both be 1, so we're not going to do that. If D is 1, then we're going backwards, and we want to toggle B off of A prime. So if I go back and look at this table here and look at the down, so notice here, down is running, B is 1, A is 1. So A is 1, so now A needs to stay the same. Or excuse me, A is 1. Wait, this doesn't make any sense. 7. What has happened here? I think there's a typo in this diagram that came out of the textbook. Because we shouldn't be going down. Oh, never mind. We're looking at it backwards, I think. Yeah. So if we're at, I was going from here to here, and that's not how it works. Right. So here, if it's B is 0, A is 0, then nothing changes, right? D is going to stay, or excuse me, A always toggles. A goes from 0 to 1. B is looking at A is 0, so in this case, B toggles and goes to 1, and then so on and so forth. Sorry, I got a little tripped over myself through that. But here on the next one, if we have 0 and 1, right, A is always going to toggle, so we're going to go to 0. But now B is looking at A prime. Here it's 1, so we're going to stay the same, and it's going to live at 0. That was a little esoteric. Now let's look at C. Right, remember C was what? C XOR BA, and again we have C XOR U and BA, or D and BA, B prime, A prime, which of course is, you know, D, B or A prime. All right, so if both of them are 0, then we toggle, whereas here both of them are 1, then we don't do that. So any questions about these equations, right? It's not super important that you know how to derive them for the test, but that you understand their behavior. All right, let's take a look at this guy, binary up-down counter. Well, this is what we just worked on. So here we've got D and U through the XOR tied around to A, so that means that A is equal to A XOR D or U, right? That's our U, that's our XOR D or U. Then we've got an AND gate here that's tied around to A as expected. Boom. And then here we've got another AND gate, so that's going to be UA. We've got another AND gate that's got D that's tied around to A prime. So that's going to be D and A prime. Through an OR gate gets us D and A prime, or U and A. And finally, through an XOR gate with B, gets us B XOR DA prime or UA. All right, now we're looking at the third one. We've got an AND gate that's tied to what? First we have, what do we got? We got B. We got A, so that's going to be U and B and A. Then I bet this is, so a D and A prime. I bet that's going to be, yep, that's going to be B prime. So that's going to be D and B prime and A prime. Through an OR gate gets us D and B prime and A prime, or U and B and A. Through an XOR gate gets us D XOR all of that stuff. So that's how we lay down our binary up-down counter. Any questions about this guy? So Liam asks, or he says, I've used up-down counter ICs before, but they count up/down whenever some input goes from low to high. Is there a way to get those using these, or are they completely different? Yeah, so this is all, so the up-down counter has all of this as the internal circuitry. The input that's going from low to high, of course, is the clock, right? It still needs to run off of the clock signal. So that up-down counter is going to be all of that, but you should have an input for U, an input for D, and then there's going to be an input for clock, and that's probably the input that you're referring to. It says, you know, they count whenever some input goes from low to high. So that's exactly what this is. This is what is inside those up-down counter ICs. Cool. All right. So now let's take a look at a loadable counter with count enable. So this is going to be similar to that parallel load shift register that we looked at, but this is a counter. So we've got a couple of inputs. We've got CT for count. We've got LD for load. We've got clock. We've got 3 inputs and output buses. Still C, B, and A like before. Now notice that clear is attached to a bubble, which means that it's going to clear on the 0, which takes us to that first row in the truth table here. Clearing is equal to 0, which means it doesn't matter what load and count are. The next state is going to be 0 no matter what happens. Everything's going to be locked into 0. So that should put a thing here that says clear. Right? Then if clear is equal to 1, then we've got some options. Some things can happen. The first one is if load is 1. Here they've given load priority, right? So if load is 1, count is a don't care. Then we're just going to load our inputs from D into Q, right? When load happens, that's going to happen naturally. Then if they're all 0, then nothing changes, right? The next state is the previous state. There's no change if it's all 0. And then finally, if load is 0 and count is 1, then we start counting, right? Then it's going to be, you know, 0, 0, 0, 0, 0, 1, 0, 1, 0, all the way down to 1, 1, 1, and then back to 0 again. So what makes this one special is that it can load, you know, we can say, hey, let's go ahead and start at 5 and count from there, right? And there's plenty of reasons why you would want to do that. This is obviously is really important in computer architecture when you want to say, you know, you need to execute the code that exists at line 53, right? You need to sort of take the counter and point it to line 53. And then once that line is done, you go to line 54, right? So the program counter is a parallel loadable counter. Any questions about the gist of this counter, right? What's important to me is just that you understand the basic operation. If I ask you, you know, sort of a basic exam question would be like, you know, if, let's say, here we go, we'll do this as an example, make sure there's nothing else. Yeah, never mind. So if I say in a loadable counter with count enable, if, you know, the present state, you know, C, B, and A is equal to 0, 1, 0, clear in is equal to 1, count is equal to 0 and load is equal to 1, what will the vector that has C plus, B plus, A plus be on the next rising edge? So this is an example of a test question that might come from this slide. So in a loadable counter with count enable, if CBA is equal to 0, 1, 0, and then clear in, I need to add some stuff too. Let me see, I forgot one thing here. I'll put it there. Oh, not there because you can't see it. I'll put it there. And let's say DC DB DA is equal to 1, 0, 1. What will C plus B plus A plus B on the next rising edge? Somebody want to wager a guess? Nobody wants to wager a guess. Kaylee says, well, wouldn't it stay the same because count is 0? Now, count is 0, but what is load equal to? In this question, load is equal to 1. Yeah, so it'd be 1, 0, 1, right? So if load is equal to 1, then we're doing the load condition, which means that we're going to grab whatever these guys are, which in this case is 1, 0, 1. Yep. So, there we go. That'd be answer choice B. DC DB DA equals 1, 0, 1. All right, any questions about that question? All right, so let's go ahead and unpack the equations. Let's just kind of go through the equations. These are a little bit tricky and they don't make a ton of intuitive sense, but here we've got A plus is equal to not load and A, right? So if we're not loading, we're going to get A, or load and DA. That makes kind of sense. And then we're XORing it with not load or load prime and count. And then for B, we got load B and then load. So this is all going to be the same, right? Not load prime and B, load D and BN, XOR LD prime and count and A, right? This is the same thing as the binary counter, right? And then on C plus, we got LD prime and C, or LD and D, C, LD prime count, or XOR, LD prime count, and B and A, just like it was in the binary counter. So you can still see those sort of reflections, not reflections, but sort of the presence of that counting behavior. You can see that in the equations, hopefully. So that's that. This one's looking all, because I added some stuff to hide these. That's what's going on. Sorry, I had to delete the annotations from the 11 o'clock lecture, and it also deleted the places where I cleaned up the screenshots. So here's what the circuit looks like. We can kind of unpack it a little bit. We got clear in doing its thing. We got A doing, clock doing its thing. Here on A, notice that we've got our A coming back around to a multiplexer now, with load as the selector. And so if its load is equal to 0, then we don't want to load. So presumably that's going to take A in. And if load is 1, then we want to grab D sub A and pass that to our XOR gate with our LD prime and count, right? And we'll see that behavior thrown over here, right? So on B, we got the mux 0 and 1 is still going to be B, or load DB. And then we got and A, or this business, LD prime CT. And then finally on C, we've got C0, DC in at 1. Still got an XOR gate. Then we got and with A and B and that business. So any questions about the circuit diagram here? The only real interesting bit is the presence of this multiplexer that lets us select between loading and not loading. All right, the last thing we need to count, or to look at, is a thing called a graph counter, and we're going to design one with D flip-flops. A graph counter roughly means a counter that counts any sequence that isn't normal counting, right? So a regular counter just counts 0, 1, 2, 3, 4, 5, 6, 7, and so on and so forth. When we say a graph counter, that means we have to specify the graph. We have to specify the sequence that it has to go through, right? In this case, we're going to go from 0 to 4 to 7 to 2 to 3 back to 0 again, right? So this has a bit of a strange behavior. But we're doing it with D flip-flops, transparent flip-flops, which means that we really just need a very simple state table here. And then the input combinations that don't appear in the graph, such as 1, 5, and 6, become don't cares. So don't care. All right. So we lay down everything like we did before. We'll say C plus is equal to the sum of minterms 0, 4, well, just 0 and 4, or the sum of don't cares 1, 5, and 6. And let's see, C plus would be the sum of minterms 2 and 4 and 7, 2, 4, 7, or the sum of minterms 1, 5, and 6. Oop, that should be B plus, not C plus. And then A plus is equal to the sum of minterms 2 and 4, or the sum of minterms 1, 5, and 6. So we can take these guys, we can throw them into a K-map like so. Here we've got C plus, we've got 1, 1 on the top row, but we've got don't cares in the second row, so we can group all of these guys into a box and say that C plus is going to be equal to what? Just B prime. And then we've got on B plus, we've got not quite as cut and dry, but we've got this column of 4, which is going to give us just B plus is equal to C, or we can create a group of 2, so C or B A prime, and then finally A plus. Let's see, we're going to have, there's a couple of different ways to do it, but I'm actually going to do it this way because it's going to lead to a better solution. So if we're taking these top ones, it'll be, what, C and A prime, or taking the bottom row, that's going to leave me with B and A prime, which I can simplify slightly to just be A prime and C or B. Like, yeah. And there we go. There's our equations, our characteristic equations for C, B, and A. All right. So there's our equations. We got them listed here. They just showed us some of the simplifications. C plus is equal to B, B plus is equal to C or B and A prime, and A plus is equal to A prime and C or B. And if we go to drop them in, starting on the right-hand side here with A, we got C or B, so that's C or B. Through an AND gate gets us A prime and C or B. This is what we expected. Here we have an AND gate with B and A prime. Through an OR gate gets us C or B, A prime, and of course DC is just tied to B prime. So this will produce a counter that doesn't count in a way that makes sense, right? It's just counts through this specific graph, which is why it's called a graph counter. So a graph counter you can think of as just being any arbitrary sequence of input combinations. And I believe, look at that, went through pretty fast. That is it. So just to recap, we talked about the synchronous binary counter with T flip-flops. We did the binary counter with D flip-flops. We looked at a binary up-down counter. We looked at a loadable counter with count enable. And we did a graph counter with D flip-flops. So, are there any questions, comments, or concerns? I see some folks are typing. Could you find the CBA plus for a regular binary counter using the same logic? Yeah, you absolutely could. I mean, you just have, I mean, if I go to this blank screen, you know, if so, that would be what, C, B, and I won't do the whole thing, but it'd be, well, I might do the whole thing. C plus, B plus, A plus. Right, so you'd have 0, 0, 0 leads to 0, 0, 1, 0, 0, 1 leads to 0, 1, 0, right, all the way down. And so, yeah, you would do the same thing, right? Down here at the bottom, you would have 1, 1, 1 leads to 0, 0, 0. And so you'd have, you know, just like before, right? C plus is a function of C, B, and A, and is equal to the sum of midterms, whatever those are. Liam asks, will you have pictures of the different circuits on the test, or do we need to know what all the flip-flop counters, registers look like and behave as? There may be pictures depending on the question, but you should be prepared to just recognize them from their name. So what I recommend, one of the things you can do when you're preparing for the exam is, remember, you're going to have your notes in front of you, is I would, you know, come here. I mean, obviously for like a graph counter, I got to give you the graph, right? And stuff like that. I've got to give you some information for a multiple choice question there. But for something like this, the loadable counter with count enable, well, what I would do is I would sort of have my notes laid out and say, all right, loadable counter with count enable, have your bullet point behavioral stuff about it. Make sure you know about that one in your notes, so that way in a question I might just say, in a loadable counter with count enable, and ask the question without showing you any pictures. You're going to want to like quickly like flip to your loadable counter with count enable notes. So because it is still an open book, open note test, I'm going to say you should be prepared to just go off the names of things instead of being shown pictures of things. No problem. But yeah, but you should definitely be able to like be familiar with the names, right? Because you're not going to have a lot of time on each question, so you want to make sure you kind of know the gist, and you kind of know, all right, you know, this page has this counter on it, and here's my stuff for it. So, are there any other questions? Cool. Well, in that case, I'm happy to let us all go and start the weekend 10 minutes early, except for those of you guys who have a physics test coming up right next. Good luck on that test, those of you all who are taking it. You're welcome. Do well. Make me proud. All right. Thank you, Aaron. You have a great weekend as well. You're very welcome, Isman.